morning, good afternoon, good evening, and welcome to the AI for Good Global Summit. My name is Bastiaan Kwast from the ITU, the International Telecommunication Union, and it is my privilege to introduce today's session, Steps Towards Trustworthy Machine Learning, with Professor Thomas Dietrich from Oregon State University, as part of the Trustworthy AI series hosted by Wojciech Samek, head of the AI department at Fraunhofer HHI. ITU is the United Nations Specialized Agency for Information and Communication Technologies, and is also the organizer of the AI for Good Global Summit, together with 38 UN sister agencies and co-convened with Switzerland. For today's discussion, we'll be using the Q&A functionality, which you can find at the bottom of your screen. Additionally, there's the chat functionality, which you can use to speak to other participants. Please make sure to select that your message is sent to all panelists and attendees. And with that, it's time for me to hand it over to our moderator, Wojciech Samek. Hi, Wojciech, how are you?
Hi, thank you very much for the introduction. Yeah, it's an honor to introduce our speaker today, Thomas Dietrich. He is a distinguished professor emeritus at Oregon State University and one of the pioneers of the field of machine learning. He has authored more than 200 papers on various ML topics, including robust and trustworthy machine learning, has received various awards, and has devoted a lot of his lifetime to service to the research community. We recently got acquainted when working on a review paper on anomaly detection together, and I must say that I really enjoyed the collaboration with you. So it's an honor to have you in the workshop series, and I'm looking forward to learning about what you think about trustworthy machine learning. So thank you for being here. I hand it over to you now. Thank you.
Okay, thank you very much. Let me bring up my slides. It's wonderful to have this opportunity to talk to a sort of worldwide audience and about the work we've been doing recently at Oregon State on at least two aspects of trustworthy machine learning. So, of course, this is the result of a big collaboration, involving some students and former students. So Jesse Hostetler, Majid Alki-Taligan, and Siliu Rishit Garapale were all students working with me and my colleagues. And Kim Meyer-Hall got her PhD working with Joe Albers, who's now a professor at the University of Wyoming and is an environmental economist. Alan Fern is a colleague of mine in computer science, and Debashis Mondal is a professor in statistics. So the talk is going to be in three parts. I'm going to start first with, I call it part zero, a motivating overview of what I view as kind of the roadmap for trying to build AI systems that are robust and trustworthy. And then after being up in the very high level overview, we're going to dive down to two fairly technical topics. One on the area of competence modeling, right? I think an important idea is that an AI system needs to have a model of its own limitations and its own capabilities and be able to communicate that. And so I'll show how we can get, before we turn on an AI system, before we press the go button, we can get a prospective prediction or explanation of how the system is going to behave, so that we, as the humans overseeing an AI system, can make an appropriate decision about whether to trust it in a particular context. And then the second part is going to be looking more at after a system is running, but it encounters something new in the world, how can it respond, and can we give any kind of guarantees that it can do that correctly? So in both of the technical things that I'll talk about today, I'm trying to achieve some sort of a mathematical guarantee that we can trust the system. Okay, so let's start with the starting point is some work that was done in management science back in the 1980s and 1990s, primarily at UC Berkeley, by Todd Laporte, Gene Rocklin, and Carlene Roberts. And a nice sort of summative review of that is a paper by Weick et al., which I cite in the conclusions here. And what they were interested is in understanding how certain human organizations are able to achieve very high reliability even though they're operating in high-risk settings. So they studied air traffic controllers, they studied aircraft carrier flight decks, and they studied nuclear power plant operators. And despite the occasional accidents that happen in all of those settings, they achieve remarkably low error rates compared to a lot of other organizations. And so what they found was that these kinds of organizations follow 5 practices in their work that they, Laporte et al., credit with achieving those low error rates. Probably the most important thing is that they start with this preoccupation with failure. They believe fundamentally, their prior belief is that the system that they're using, and I use system sort of in the larger sense of the human-machine system, that it has unobserved failure modes. And so part of their goal is to try to detect those failure modes before a full failure occurs. And so they are constantly watching for anomalies and near misses and treating those as symptoms of a potential failure mode in the system. When they encounter an anomaly or a near miss, they exhibit this reluctance to simplify interpretations. That is, they comprehensively try to understand what are the different possible explanations for the anomaly or the problem. This usually requires having a diverse team with a wide range of different expertise, right? It could be that the person that understands the problem in the nuclear power plant is actually the janitor or someone who has very low status in the organization. And then the third thing is what they call a sensitivity to operations. I think we would, in computer science, we would call this situational awareness, that there's a subpart of the organization whose only responsibility is to maintain continuous situational awareness of what's going on in the system. The fourth is that these organizations practice resilience. So they develop a capability to detect, contain, and recover from errors, and they practice improvisational problem solving. And then finally, the principle actually that has probably had the biggest impact is called deference to expertise. And the idea here is that during a crisis, authority should migrate to the person who can solve the problem, who has the necessary expertise, regardless of their rank in the organization. So for example, managers should never be making the critical decisions. And so two of the most important consequences of this line of research have been the patient safety movement in hospitals, in operating theaters in hospitals. And the idea is that anyone on the surgical team, a nurse, the student in training can call a halt to the surgery if they see a problem. So they're all empowered to intervene. And similarly, the other area is known as cockpit resource management, but it is trying to give the co-pilots and the sort of lower status people in the cockpit techniques for breaking into the pilot in command, into their consciousness to try to call their attention to problems. So a big problem that's happened a lot in aircraft is that the pilot gets preoccupied with one particular aspect of a problem and loses situational awareness about something that's potentially much more important. So pilots have crashed planes because their head is down and they're thinking about some technical issue. So this is, I find this very inspiring because I can think about building on this in two directions. One is if we're trying to build an entirely autonomous AI system and we want it to be robust or highly reliable, how can we have it perform all 5 of these functions? And secondarily, I believe that in general, it's very rare that we want to have a completely independently operating AI system. Instead, we're usually looking at a case of teamwork where there's a human organization and an AI system or multiple systems working together. The human team is often overseeing and complementing the AI system and vice versa. And so then what do these 5 principles tell us about how we should design those systems? So I thought I would go through the sort of current state of our AI technology and give a sort of scorecards for how we're doing. So when I think about it from the AI standpoint, I think about 4 different properties. The first is maintaining situational awareness. And this is one of the areas where I think the AI systems have potential to give superhuman situational awareness, because AI methods are very good at integrating data from multiple data sources, multiple sensors and effectors, and using that to maintain an estimated probability distribution over what is the current state of the world, the current state of the system, and so on. The second is that we need to be able to detect anomalies and near misses in our operations. And there's quite a lot of research over the last 20 years or so in statistical anomaly detection. And I will actually touch on that a bit in my talk later. There's less research on identifying near misses. I think our AI systems tend to view that if they get the right answer, then everything was fine. And so I think there's research needed there. A third thing is then, once you have an anomaly, can you generate candidate explanations for the anomalies and near misses? And this is an area that has been touched very little. We have systems that can diagnose failures, but within a sort of known failures. So when we have unknown failures, how do we diagnose those? And finally, systems that can improvise solutions. What would it mean for an AI system to engage in improvisational problem solving that somehow can extend the space of possibilities beyond the initial problem space that the system was programmed with? So in terms of a credit card, I would say we get an A for situational awareness, a B perhaps for anomaly detection, but we're getting failing grades, I think, on being able to explain anomalies and to improvise solutions. Now let's turn to the scenario where we're looking at an AI plus human team. I think the situational awareness, again, the AI system probably can do a very good job of this, but that's not sufficient in a team. The AI system and the humans need to establish and maintain a shared mental model of the situation. So how does the AI system help the humans maintain situational awareness without bombarding them with irrelevant information? And also humans, there's an additional form of situational awareness the humans need, which is what version of the AI system are we using? Was it just updated today? Was it retrained recently? So humans need to maintain their mental model of the capabilities and failure modes of the AI system, as well as I don't know, the air traffic control system or whatever it is that they're managing. On the anomaly detection side, another form of anomaly or problem is a breakdown in the teamwork between the human and the AI, or between different humans in the human side of the organization. So the AI system really needs to understand and predict the behavior of the human team. If we imagine having an AI system that could be empowered to stop operations when it sees a problem, when would we really want to trust it to do that? And what would it need to understand about human behavior? Generating candidate explanations, same problem we had before, but now could we build an AI system that could assist humans in doing that? And the same with improvising solutions. What would it mean for an AI system to support human improvisational problem solving? There's one area of what's called mixed initiative planning, where this has been studied. And now we're seeing a lot of applications of artificial intelligence in the arts. And so maybe we can learn something from improvisation in performance art, for example. So I think our credit card here, we don't have any A's or B's. We definitely have C's and D's. And there's a huge amount of work that needs to be done. Okay, well, that's sort of my very top level motivation. Now we're going to dive down into two different specific settings. The first one is competence modeling for prospective performance guarantees. So prospective meaning giving a guarantee in advance. So imagine that I'm a human decision maker, and I must decide whether to command my AI assistant to go ahead and act autonomously for H time steps. So I'm this black blob here, and here's my AI system. And the world or the system that we're managing is in a particular starting state, S naught. And I say it's an MDP, that would be a Markov decision process. That means that the system we're controlling, we have full observability into its state. And its behavior depends only on its state and its ability to perceive the state of the world. So what I want to do is the human, it wants to ask the system, starting in state S naught, how will you behave? What kind of strategy will you follow? And what the system is to provide back is some sort of what we call a trajectory-wise prediction interval. So the idea is that time is on this horizontal axis here, and this we have some measure, some variable that characterizes the behavior of the system, how fast it will be moving, how much energy it will be consuming, something like this, and we plot an upper bound and a lower bound on that quantity over time. And what we want is a guarantee that the true trajectory that the robot follows, that the system follows, will fall inside these bounds with probability 1 minus delta, where delta might be, 0.1. So we have a 90% guarantee that this trajectory is a faithful description of the future behavior of the system. So now the human can look at this prediction and say, looks good, and press go, or maybe the prediction is very wide and there's a very high risk of failure, then the human might want to not trust the system, but take the controls themselves, or maybe there are other fallback strategies they might engage that are outside of the understanding of the AI system. So the approach that we take basically is to assume that at training time, we can sample starting states from some starting state distribution. And then in each of those states, and this would often be in a simulation, but in each of those states, we can execute this control policy pi. We can execute it for h steps, in this case, 50 steps, and we can get the actual trajectory that the system followed. And so this is for a biological control problem of an invasive species data, because from from the sort of AI for good area, I mostly have worked in biological conservation, wildfire management, invasive species management, things like this. And so these are a sort of unusual kind of control problem because we're trying to manage an ecosystem. And so we have some measure on the vertical axis, which is, say, the cumulative reward that we've experienced so far. And in this case, the rewards are all negative because they involve an invasive species causing damage, or me spending money trying to prevent that damage. Okay, so here I have, say, 50 trajectories or 100 trajectories, and this is my training data. And then we're going to apply our new technique that consists of 2 stages. The first step is to compute to perform what's called quantile regression. So out of all of these hundreds of trajectories, we are going to calculate, say, the 90th quantile and the 10th quantile. That would give us an 80% coverage interval. Or maybe we need the 95th and the 5th quantile. That would give us a 90% interval. Or maybe even the 99th and the 1st, which would give us a 98% interval. In any case, we perform what's known as quantile regression, which is a bit like standard linear regression, except that it predicts these quantiles, the extreme values of the distribution, rather than the average. And our notation here is ft to the -1 is ft is the traditional notation for a cumulative distribution function. And so it says, given that we're in state S naught, and we want the delta over 2, so if delta was 0.1, we want the 0.05 lower quantile. We want the value of this performance indicator, this cumulative reward in this case, that we would see in the 5% worst trials. And this one would be the value that we would see, the 1 minus delta would be the 95 percentile, that would be the 5% best trials, right? And so those gives us these kind of gray dotted lines here. And I'm plotting for a particular test trajectory because the predictions here depend on the starting state. So in this case, this is actually a really nice trajectory. And we can see that very rapidly we're going to stabilize the system, and then we have sort of a minor amount of additional expenses that we incur over time. But unfortunately, quantile regression, while it is a beautiful thing, does not give us any kind of statistical guarantee that the system will actually be inside those bounds. In fact, we're computing the quantile bounds independently at each time step. And so even if it gave a guarantee at each time step, it wouldn't give us a guarantee for the entire 50 time steps. So for that, we have a new method that's based on something called conformal prediction. And we calculate a sort of additional correction, which are the green dots here in this picture. And these give us a probabilistic or statistical guarantee that in 1 minus delta of the trajectories will lie inside those green bounds. So that's the idea of this approach. Okay, well, how does it work? Well, let me talk a bit more about quantile regression first. So let's suppose we have a simple, just one-dimensional problem. We have an input X that leads to a system response Y, and we want to predict P of Y given X. So standard linear regression would just predict the mean value here. But we can see that this problem exhibits what is known as heteroscedasticity, right? That's a wonderful Greek word we love from our introductory statistics class, that the amount of variability depends on the value of X. Down here, when X is small, the amount of variability is tiny. When X gets up here, the amount of variability is large. Okay, and so one way to deal with variability is to actually predict the quantiles of the distribution. So what quantile regression gives us, if we plug in the target quantile being Q of 0.9, then we're supposed to get a regression line such that 90% of the data points lie below the line and 10% lie above the line. And if we put in 0.5, we're hoping to get the median with 50% of the points above, 50% below, and so on. So that's the idea of quantile regression. Now, there are several quantile regression algorithms that have been developed over the years. We're employing something called quantile random forests, which make no assumption about the nature of the curve, the prediction curve. It could even be discontinuous, from Minshausen from 2006. Okay, so now to apply quantile regression to trajectories, we need to start with, say, a discrete time Markov decision process. It could have continuous state space and continuous actions. So it could be like an aircraft or a robot or something that's moving in space, or a medical system that is controlling, say, the amount of oxygen being administered to a patient or the amount of anesthesia or something like this. And we want to run it for H steps, this policy, this fixed control policy that has been produced by humans or by training a machine learning system or whatever, but it's a fixed controller. We collect sample trajectories, and then we define some kind of behavior function, a thing we're interested in measuring. And it could be the state variable, like the amount of blood oxygen, or the amount of power being produced by a power plant or something like this. It could be the immediate reward if there's some cost or penalty. It could be the total reward that we've received since the starting state. And that's actually the one that I'm going to use, the cumulative reward. Start from the sort of historical cumulative reward up to now. If we're thinking about value functions, for those of you who are familiar with reinforcement learning, we could be trying to predict the future reward. So we would be looking at the value of the value function as a function of time. But whatever it is, we get what we'll call boldface B of tau. Tau is the trajectory that was followed. That's the historical record of everything, the states, the actions, the rewards. And B of tau is going to be a behavior vector that I'm plotting here as these red curves. So now we can fit quantile regression functions at each time step independently, and we get the black or gray sort of dotted lines that I've shown there. Now, the key thing is that these are a function only of the starting state S naught, because we want to give this prospective guarantee that to the human decision maker at time 0, how is the system going to behave? So that gives us this quantile regression prediction. But as I said, it doesn't give us a guarantee. So how can we get a guarantee? Well, we're building on a beautiful work by Romano, Patterson, and Candes from NeurIPS 2019 on what's called conformalized quantile regression. And the idea is that we're going to think about computing an error, I'm going to put it in quotes, between, say, the predicted quantile and the observed value. So if we think about, at this point here, that black dot is above the blue line by some amount, and we're going to call that C sub I. So if this is yi here, we'll look at this yi here, and we'll subtract off the predicted value given xi, the predicted value of that curve. And we'll call that C sub I. It's the, I don't know, the correction, let's say. And of course, we believe if the quantile regression works correctly, then say, in this case, 10% of the C sub I values would be positive, and 90% of them would be negative. But in any case, what we're going to do, we're going to assume that we actually, I should back up a little bit, assume we have 2 data sets now, or that we've taken our data and divided it at random into 2 subsets. We use data set D1 to fit this the blue curve, and we're going to use data set D2 to do this conformalization correction to it. And so we've calculated these corrections, these CIs, and then we sort them into ascending order. And then we calculate, we take the element that is the, if we had n of them, we take 1 minus delta, which is the guarantee we want, times n plus 1, and its ceiling, so the next larger integer, and we take that element of this sorted list. So if 1 minus delta was 0.9, we would take 0.9 times n plus 1, and that would be the 90th element if this list had n plus 1 elements in it. It doesn't, it has only n, so we might have to round up to the next larger element in the list. And that's going to be our high bound on this, and it'll give us this red correction. So this is a constant value that's going to be added for all x values. It's going to be added to the curve. Now, the sort of proof for why this gives us a guarantee is the following kind of thought experiment. Let's let xn plus 1, yn plus 1 be a new point that we didn't use in training. And if we calculated its correction value, its cn plus 1, the first thing is to notice that these ci values that we're computing are what are called exchangeable. That is, the order in which we see them doesn't matter. So if we had seen this n plus first value first, and we were now looking at C1 as the new value, the process is completely symmetrical. And that's true because the starting states in our problem are drawn independently from some starting state distribution. And any randomness that happens during the trajectory follows this Markov property. So it can be treated as independent. From one trajectory to another, it's different randomness. So we could ask ourselves, well, where would this Cn plus 1 value fall into the sorted order? And the answer is that it will be uniformly distributed in the sorted order. So we can choose the element in that sorted order that is the 90th percentile of that sorted order, and use that as our upper bound. And that means that the probability that yn plus 1 will be less than or equal to that upper bound will be at least 90% in our case. So it's a very simple idea, and it's very beautiful. It's really due originally to Vladimir Volf, who initiated this notion of conformal prediction back in the early 2000s. But it's recently been taken up much more by the statistics and machine learning communities. Okay, so how do we apply this to trajectories? This was applying it just to single points, but we have 50 time points. So what do we do? Well, the idea is that I'm going to, all along at each time step t, we're going to calculate what I'm now going to call an exceedance. So instead of a c value, I'm going to have an x value here, which is if the quantile regressions predicted these black dots, the black curves, and I have a training trajectory from D2, my conformalization set. If it is outside the black dots, then I'm going to calculate an exceedance. And that's going to be the maximum of 0, or if it's going below the lower bounds here, or above the upper bounds. See, there it is. Below the lower bounds, or if it was up here, it would be above the upper bounds. If it's inside, it's 0. So we'll call those our exceedances. And then what we're going to do is, because there's different amounts of variability at different times along the trajectory, we're going to rescale the exceedances by the variance, estimated variance at each time along the trajectory. So we're going to assume we have access to a small additional data set, maybe 50 or 100 points. We don't need too many, to estimate sigma hat at time t, which is the variance at each of the time steps t. And then we'll rescale our exceedances xit to be x prime it by dividing by the variance. Or if the variance is 0, then we just set it to 0. And then we can calculate for each trajectory, what was the exceedance that was the worst one, that fell outside the quantile regressions by the most amount. Because we're going to try to set the quantile, we can think of these green dots here as a box, a hyper rectangle in 50-dimensional space. And CI, the largest exceedance, is going to need to exceed the limits of that box only 10% of the time or 5% of the time, whatever our target is. So we can sort these exceedance, these maximum exceedance values, and again take the define beta to be the value in that would be the if there were n+1 elements in the sequence, it would be the one that was at the 90th quantile. And so then we can correct our quantile regressions by adding and subtracting beta times this sigma hat. And so that's how we take a 50-dimensional problem, boil it down to a 1-dimensional problem, which is the maximum of the exceedances, and then calculate beta. Now, at this point, we're making very strong use of a beautiful fact, which is that conformalizing or conformal prediction is completely independent, distribution independent. It makes no assumptions about the probability distribution of these CI values. And that's a good thing because if you think about the maximum of a set of points, typically has what's known as an extreme value distribution, which has very heavy tails. And so it would be very dangerous to make a Gaussian assumption here. So we're not making that. But instead, we get a finite sample distribution-free guarantee. So we can prove a theorem here that the behavior vector will fall within the prediction interval, which depends, again, only on the starting state of some, oh gosh, I changed notation here, but tau star is going to be in a new trajectory, and B star will be its new behavior vector. And so S naught of tau star is the starting state of that new trajectory. And this depends on the bounds that we produce, because they depend on the quantile regression, depend on the starting state. And so the guarantee is over the probability of the choice of starting states and any randomness in the policy and in the MDP dynamics. This turns out to be a special case of a very general theorem that was proved by Ley, Rinaldo, and Wasserman in 2013 for general functional data. Okay, so now let's look at applying this to a couple of problems. And the first one is managing invasions of Tamarisk trees in river networks. So the Tamarisk, of course, is a tree that is native to the Middle East. But in the United States, it is an invasive species, particularly in the rivers of the western, sort of drier parts of the US. So the Rio Grande River, the Colorado River, and their tributaries, for example. So in collaboration with Kim Hall and Joe Albers and my student Majid Alki Talagan, we studied a sort of stylized version of this problem, where we think of the river network as being a binary tree. So we can think of this is a river network, and water is flowing down the screen, and the various tributaries come together, and then here it empties into the Gulf of Mexico or something. And along each edge of this graph, which is known in the river literature as a reach of the stream, we're going to imagine in this particular toy version of the problem that there's only room for one tree to grow. And so that tree can either be an invading tree, that's I here, a native tree, N, or there could be no tree growing there at all, which would be E for empty. And our time steps are years. So in each year, we have a chance to go out and apply some kind of a treatment for each edge. We could go to an empty edge and plant a native plant there to try to change an E into an N. We could go to an invaded edge and try to kill the tamarisk tree, which would convert an I into an E. Or we could do the most expensive action, try to kill the tamarisk tree and then plant a native tree, which is the eradicate plus plant option. Or we could do a no-op, which is do nothing on that edge. It already has a native tree, for instance, so we don't want to do anything there. Each of these actions costs a different amount. The no-op costs 0, and eradicate plus plant costs the most. Now, ideally, in 1 year, if we had a big enough budget, we could just go through the whole river network, kill all the tamarisks, and plant native trees everywhere, and solve the problem. But unfortunately, there's usually a very severe budget in these kinds of problems. And also our actions don't always succeed. So when we try to kill a tamarisk tree, maybe it only succeeds 70% of the time or something like this. An additional problem, and so we typically can only afford to do 1 or 2 actions, treating only 1 or 2 of the sections of the river. So, and that raises a problem because the trees each year, well, some of them die natural deaths, but generally they make lots of seeds, and then those seeds propagate through the river network, primarily downstream, and the seeds may come to rest in an occupied edge that has no effect. But if they come to rest in an empty edge, then they compete to try to get established there. And so this tamarisk tree up here could produce seeds that flow downstream and invade this edge here. And so often we end up with a case where we kill a tamarisk tree, but new seeds come and reestablish the invader in that edge. And so that's can cause the control process to take many years to complete. Well, here are some examples of the kind of prospective prediction intervals that our technique produces along with the actual trajectories. So here's trajectory 61, and I've sort of given the starting state down here, although here I use T for tamarisk instead of I for invader. So in this starting state, there were a lot of empty edges. There were 2 natives and 1 tamarisk tree. And it turned out in this case, the red curve reflects the fact that, well, first of all, based on the quantile regression and our prediction method, we get a fairly narrow confidence interval or prediction interval. It says this is going to be a good case. And the actual experience was, yes, the red curve was inside the bounds. And it turned out what happened was at the very first step, we killed the tamarisk successfully. And so then the problem was solved. In the second trajectory, we have 3 tamarisk trees and only 1 native. And in this case, it's the model predicts that there's a potential that it could take, we could incur a penalty of 40 units, and it could take a while to control the system, say about 10 years. In fact, it turns out we got lucky in this case. 2 of the tamarisk trees died natural deaths, and we were able to kill the remaining tree in 1 step, and so we got lucky there. And trajectory 27 is an example of a failure of the prediction interval. It's a starting state where there are 5 tamarisk trees and no natives at all. So we have no native seeds in the river network to compete. And so the prediction interval is already says you're going to be spending at least 20 units, and it's going to take you at least, maybe in the best case, 6 years to control things, but it could take you 10 years. And in fact, it did take 10 years, or maybe 11 or 12. I can't, reading this. But it turns out we got actually unlucky here. And in one of the edges, we had to 3 times kill the tamarisk tree because it kept getting reestablished each time. So that was a kind of unlucky run. But these are instant examples, but in practice, we generated 5,000 test trajectories. And we measure how well we're doing. And so in this plot, the vertical axis is trajectory coverage. What fraction of the actual trajectories was covered by their corresponding prediction interval, right? Because the prediction interval is different for each trajectory. And then I'm plotting results for 3 different methods. The gray bars are if you just use the raw quantile regression. The blue bars are if you use the method that I described in the slides. And then we have an improvement on that method that uses a confidence interval to estimate the upper and lower quantiles that are needed by the technique. And then we're testing for 4 different values of delta, the guarantee, and for 4 different sizes of the data set. So as we move from left to right, we're using more and more data, and we're requiring a tighter and tighter guarantee. And so what we see is that there are 16 configurations here. None of them were, if we use just a raw quantile regression interval, we don't cover any of them. But if we use either the strict or our improvement on it, either the blue or the green curves, we have successful coverage in all 16 cases. So the guarantee was held here 100% of the time, which is what we want to see. Okay, well, I guess the right way to say that is that the guarantee achieved its nominal value, if it was 0.8 or 0.9 or 0.95 in all cases. Okay, the other case that we looked at is more fanciful. It's battles in the Starcraft game. So we've trained a reinforcement learning system to play out a two-team battle between a blue team and a red team. The red forces start out on average with a disadvantage in terms of the number of units that they have. If they had the same number of units, the two sides would be evenly balanced. But the red forces start out at a disadvantage, but at time 14, they are going to receive a random amount of reinforcements. And so the question is, from the blue team's perspective, can we give a guarantee for how the game is going to unfold, even with that uncertainty that the blue team knows that at time 14, the red team is going to get a stochastic amount of reinforcements. So I won't show you the trajectories. I don't have time for that. But in this case, the raw quantile regression does achieve its stated coverage 2 out of the 16 times. So it failed very badly down here, but we can see that there are a couple of cases where it's actually doing okay. The so-called strict method also only succeeds 5 out of the 16 times. And even our confidence interval, our stronger confidence interval method only failed twice. It's informative to look at where it fails. It fails out here at when we're requiring a 99% guarantee, when the amount of data available is small, 250 or 500 data points. Once you have 1,000 points, we're doing fine. And if you think about it, to get a 99% guarantee, we have to be estimating the 0.995 and 0.005 quantiles. So those are 5 out of 1,000 cases. So you need quite a lot of data to do that. And I would say that is that's maybe one of the 2 weaknesses of this approach. One is that it requires a lot of data, and the second one is that it might be misinterpreted. We'll talk about that in a moment. But in any case, you can see that if we have enough data, then we're able to achieve our nominal coverage very well. So the methods work well. But let me come to the second weakness or issue with this method, is that it requires careful interpretation. You'd really like to say to a decision maker, starting this starting state, I guarantee that in this particular execution of the policy will be inside these bounds. And that's kind of the picture that I'm drawing when I put up those prediction intervals. But it turns out the guarantee is not that. An 80% guarantee, for example, says that overall queries, that is overall future starting states S0, if they're drawn from the same starting state distribution, then 80% of the time, the true trajectory will lie inside the prediction interval. But this is not a pointwise guarantee. It doesn't say for any particular query, 80% of the time, the actual run will be inside the bounds. It says averaged over all queries, 80% of the time, will be inside the bounds. And this is unfortunately necessary. There's a theorem from another paper coming out of Candace and Ryan Tibshirani's groups that a pointwise guarantee is impossible unless you have a lot of training data for that specific starting state. Then you can do it. So there's a risk that it can be misinterpreted. However, if you and so the risk is that there might be 20% of the starting states where the guarantee where the prediction always fails, and it's always those same starting states. And so the antidote to this is to analyze in our training data the failures and check that they are kind of uniformly distributed throughout the state space. In which case, it's not misleading to give the guarantee we're giving. If the failures all concentrate in particular regions of the state space, then we're in trouble. And so that's the next step that we're trying to pursue in our research. Okay, well, I'm running kind of, I talked too much about the first two topics. Let me give you a brief overview of the final one. And this has to do with, now at runtime, what happens when a system encounters an unknown, something novel that it wasn't trained to respond to. So let's think about a standard classification problem and imagine we're training, say, a self-driving car. And maybe we're training that self-driving car in Europe. And so the kinds of things obstacles we might need to worry about are cats and deer and maybe children on bicycles. And so we have some sort of some set K of known classes of obstacle. And our inputs xi are images, and yi is a label for the kind of obstacle that we're seeing. But unfortunately, at runtime, maybe we take the system and we actually are going to deploy it in Australia. And it turns out there are new kinds of obstacles there that we weren't trained on, things like kangaroos, for example. And so this is known as the problem of open set or open category detection, that the set of categories, our traditional machine learning systems are trained assuming a closed world of only K possibilities. And they literally partition the space of all images into K regions. So this kangaroo will be classified as one of the K known classes unless we can detect that it's something new. And I used to use this as just a toy example, but it turned out it really happened with Volvo, that their driverless cars were confused in Australia. Okay, so the method we're going to use, we call these new cases the aliens, because they're sort of alien obstacles. And we want to, we're going to reject them using anomaly detection. So we're going to train an anomaly detector that given a new image, it assigns an anomaly score, A of X. And if that exceeds some threshold, then we raise an alien alarm. And otherwise, we go ahead and call the classifier and trust its output. Okay, so the central question is, how do we set this threshold tau to try to get a guarantee that we will detect, say, 90% of the aliens or 99% of the aliens, right? And we undertook this research really trying to ask, is there any conditions under which we could give a guarantee of accuracy, of robustness in this situation? And we want to do that without having labeled data. If you give us labeled data of the aliens, then the problem is easy. But the whole point is we want to protect ourselves from the unknown unknowns. Is it possible at all? Well, if we wanted to, a starting point is to plot something like this. This is our anomaly score that our anomaly detector is assigning. And this is, say, what the distribution of those scores looks like. So for examples that belong to known classes, we might get a distribution that's like this blue score. It assigns anomaly scores between, I don't know, -5,000 and -3,000, something like that. Whereas if we had training data for the unknown classes, we could get this red curve, which shows that it assigns higher anomaly scores, which is what we want. But not always. Some of the anomaly scores are pretty low, even for the unknowns. And what we want to do is we'd like to control the missed alarm rate. That is the cases where it's an unknown, but we don't detect it. Now, to control the false alarm rate, we don't need the red curve. We can just use the blue curve. And previous research has just looked at this case. Say I only want a 5% false alarm rate, so I want to choose a threshold such that the area under this blue curve is only 5%. But what we want is to control the missed alarm rate, so we want the area under this part of the red curve is 5%. And how can we do that without knowing the red curve? Well, in general, we can't do it. But one thought is there might be one case, and it's the following. Let's assume that in addition to our training data, which we'll call the nominal distribution, which was labeled, in addition to that, suppose we have access to an unlabeled set of data from Australia that is a mixture of known classes and aliens. So aliens come from a distribution D sub A, and the knowns come from D sub 0, D naught. And then this parameter alpha is the fraction of the test points, the test queries that will be aliens. And so this is a so-called mixture distribution. It's a mixture of two distributions. So if we have that, then it turns out that we really need the cumulative distribution functions of the anomaly scores, or their densities, the curves that I showed before. It turns out that if DM is a mixture, then so is the CDF, the distribution for the mixture, CDF, the cumulative distribution function of the anomaly scores. And so ideally, we can do a little algebra and solve for the CDF of the aliens by taking the mixture minus 1 minus alpha times the nominal, and we can estimate this from our training data. We can estimate this from our mixture data. And if we know alpha, we can solve for this. And so we get this beautiful picture. And then if we want to get a 5% guarantee or a 95% guarantee, we can threshold this at 0.05 on this axis and figure out what's the anomaly score we need to use. The reality, unfortunately, looks more like this. When you fit the empirical CDFs, you get the blue curve and the black curve. But when you're subtracting them, and you no longer get a valid CDF. So what do we do? Well, we tried various things, but it turned out the best thing to do was just to say, if we're trying to get a 95% guarantee, or that our missed alarm rate will only be 0.05, take the rightmost point where the red curve crosses 0.05 and use that as our threshold T hat for missed alarm rate. That worked better than trying to convert F hat A into a legal CDF. And so then we can prove a finite sample guarantee that says that, that this algorithm that I just described will return a threshold that achieves an alien detection rate of at least 1 minus our desired missed alarm rate plus an error amount epsilon with probability 1 minus delta. So this is a typical what we call PAC, or probably approximately correct guarantee. With probability 1 minus delta, we get an answer that is approximately correct, and the approximation factor is this epsilon. And the number of data points that we need, according to the theory, scales like this, or maybe it's better to write it in big O notation: 1 over epsilon squared, 1 over alpha squared, log of 1 over delta. So this is the typical kind of dependency you get, a 1 over epsilon squared dependency. And this assumes that we have the same number of data points for our training data and our mixture data. We can generalize this easily to handle the more general case. Okay, well, I won't go through all of the details here, but the theorem assumes that we know alpha, the mixture proportion. If we don't know it, it is possible to estimate it, although we can't estimate it with a guarantee of getting an upper bound, which is what we would need. We can estimate it with a guaranteed lower bound. But the estimates turn out to be pretty good. And so we have a paper under review where we compare a bunch of different estimators and choose the one that works best. And I can't give you all of this. Let me just say, in practice, how well is our recall, that is our detection rate, and our false alarm rate, or false positive rate, on some benchmark data sets. And we're varying here the fraction of the aliens, and we see that, and the gap between the desired coverage, which was 0.95, and the achieved coverage, that's basically the epsilon in the theorem. And we can see that when alpha is small, epsilon grows because we have a fixed amount of data. But as alpha gets larger, we do better. And for only one of the data sets, which was the space shuttle data set, which is pretty large, were we able to really do super well. We had epsilon was basically 0. But for the others, we're doing reasonably well. I mean, we're getting a 90% guarantee, even though we were requesting a 95% guarantee. And that's that epsilon gap. And you can actually take that into account when you're choosing the quantile. You can ask for a more stringent quantile in order to get something that the target you want. Okay, so let me conclude. Just a reminder, I started by talking about high reliability organizations and the management science studies of those. as an overarching framework for thinking about how we can build trustworthy AI. And then we drilled down to two, I would say, component or supporting technologies for that. One is having systems that can give a prospective guarantee or explanation of how they're going to behave, so that the humans in a human AI team can decide whether to trust the AI system or not. And the second was, how do we make that system, when it is operating autonomously, to deal with unknown unknowns. And we gave one example where we can give a theoretical guarantee for the missed alarm rate, and a practical algorithm for estimating the novelty proportion and for trying to set that alarm threshold. So I will conclude here by thanking the National Science Foundation, the Defense Advanced Research Projects Agency of the US, and Huawei, who provided a gift for this, and my colleague Kiri Wagstaff and some anonymous reviewers for their feedback on the methods. And in the slides, which the organizers have available, I give various citations for the relevant research. So I'll back up here and be happy to answer questions.
Yeah, thank you very much for this excellent talk. We have a couple of questions in the Q&A. So I think the first one is about this CQR. So could you comment a bit on the connection between the exchangeability assumption made in CP and non-IID data? So what are the limits of CQR when the data generating process changes?
Okay, so that's an excellent question, because both of the techniques I described here assume that the world, in some sense, is not changing, right? So our training data that we collected, that we did our quantile regression, and then we did the conformalization, and then our future test data where we're going to be making these predictions, we assume that they're coming from the same distribution. And that's a huge weakness. And obviously, we would need to be part of the situational awareness question, I would say, for AI systems, is the need to be monitoring the data, looking for detecting change in that, and so doing change detection. And of course, that's a fairly mature area in statistics, but I think there's still a lot of scope for more work there. And so both of my techniques totally are making that stationarity assumption. And that's I really think we need a new kind of machine learning that tries to model the trends in the world. How is the world changing? Can we anticipate those changes? And we might call it dynamic machine learning or something like that, non-stationary machine learning. We need to do a much better job of that. And of course, the people that work in time series forecasting, they do this all the time. So we have a lot of lessons we can learn from that.
Thank you. So another question also applies to the CQR method. So you mentioned that the training set is used to fit the random forest model on the curve, and the calibration set is used to compute the intervals.
Right.
So if you have a new unseen data point, can we use the same random forest model to predict the intervals for new points, or are the intervals produced just once?
No, we use it to, we actually have to use the quantile regression to predict the new intervals, and then add the conformal adjustment to them, and that's how we get our prospective guarantee, our prospective interval. So we need the quantile regression at runtime to. That's the part that actually is conditioned on the starting state, and the conformal adjustment to it is the same for all starting states. And so, but I should say that any method that produces a prediction interval can be conformalized. So it doesn't really even need to be a quantile regression. So there has been work in the machine learning community, especially with neural networks, where you have the neural network output predicted upper and lower bounds by some means, maybe estimating the mean and the variance, or various other techniques. And you could certainly use that, but again, you'll need that at runtime to get the predicted intervals, and then you'll add the conformal correction to them.
Mm-hmm. So one question which I have. So I think in the beginning of the talk, you said that like the area of explanation is at the beginning explaining anomalies and outliers is still a big problem. And I know that you are aware of the work we are doing here in Berlin with LRP and applying it also to anomaly detection. So in your view, what do you think is missing? I mean, what would you like to have to give this point an A instead of a D?
Oh, that's, yeah. So certainly in, say, like the image, detection problem, right? The explanation that we can give, it would be nice if it could say, oh, this seems to be a new kind of object, and here are the things that I can see that are different from my training data. I don't know, it has a long tail, or it bounces vertically, or something like this, right? So it'd be nice to be able to express those features. And of course, that is the big challenge in anomaly explanation, is to explain it in terms of good features, because the features have to be features from our training data. And if our training data didn't have anything that bounces vertically or has long tails, then we don't have that vocabulary. We need to get it from somewhere. And so part of the solution, I think, is we need to have much broader training, so we have a richer vocabulary. Either that, or we have to hand engineer that richer vocabulary by bringing in domain expertise. In the reinforcement learning or dynamical case, you would like to maybe be updating your dynamical model of the world and saying, oh, the reason this failed, it's some sort of new failure mode, and what happens is the wheels on my robot stops turning, and that's what's causing the problem. So yeah, and I don't know that people have looked at explaining dynamical anomalies in dynamical systems. That would be, yeah. So, but you're right, we are making progress. I mean, we also have done some sort of feature-based explanation work, but again, we assumed we had the vocabulary and we didn't have to discover it. In a deep learning case, you have to learn the vocabulary too. So it's hard.
So another question from the audience. So would it be possible to classify unknown samples by simply setting a threshold for a classifier? So if none of the categories predicted is better than, say, some threshold, the sample is classified as unknown.
Right, and so actually the sort of baseline method for anomaly detection is just to look at the predicted probabilities of the known classes. And if the classifier says, well, I don't have strong evidence for any of my known classes, so I'm predicting something close to the uniform distribution, then that is an anomaly signal. Unfortunately, it's not necessarily a very strong anomaly signal. The trouble is that when we train our classifiers in a discriminative fashion, we're telling them that they can focus on just the things that allow them to distinguish among the k known classes. Those features might not be enough to distinguish among new classes. And this is actually, I experienced a sort of version of this. I had a project on trying to recognize insects from images for another biological problem, surveying river networks, measuring the insects that live in the rivers. And we had 54 classes of insects that we wanted to recognize. And we built a beautiful computer vision system. It was pre-deep learning, but back around 2005, they could do pretty well on these 54 classes. But it turned out that in our actual field samples, there were many more categories of objects that we hadn't planned on. And we had made a sort of a methodological blind decision. We had said, well, among our 54 classes, color is not a useful feature. So we'll just use grayscale images. And so, but when it came to recognizing these anomalies, color would be really valuable. So we did that as engineers making that mistake. But that's exactly what machine learning algorithms do too. They may figure out, I don't need color to tell the known classes apart, so I'm going to ignore color. And yet then you get an insect that looks like one of your insects, except that it's bright red, and you don't even notice it. And so that's why, or that's sort of the challenge, I'd say, for you, especially with deep learning, but even for the entire engineering pipeline, to include everything that might conceivably be relevant in the anomaly detection system. And then you have this problem that you now have a very high dimensional system and you need more data to train it, and it leads to big challenges.
So do you think we need to move towards more like a generative model and
yes, generative models, yeah, right.
Composed?
I mean, as you know, in our review article, we talked all about that we're really trying to estimate the level set of a generative probability distribution. And that is sort of the right thing from a theoretical standpoint. But of course, what we see in practice with these deep generative models is they exhibit many of the same problems that the discriminatively trained models do, that they often assign higher likelihood to things outside the training set, because they're learning a representation that was sufficient for the training data, but not necessarily sufficient for the test data. So yeah, I'm beginning to be very skeptical of using learned representations in anomaly detection. Maybe we should use representations that are not very much learned, or are learned on huge amounts of unlabeled data or something. The representation problem, I think, is the central challenge.
So do you think we can force the model to learn more meaningful representations, for example, by multitask learning? So I have the feeling that if a model is forced to solve several tasks and not only one task, it is forced to learn more meaningful representations.
Right. And so, yeah, so that's the very natural approach, is to say, well, let's force the system to represent lots of things. The other approach is more like the reconstruction approach, which is, say, we want to keep the system from forgetting anything, so it has to remember everything. Then the trouble with the remember everything strategy, which is also the kind of generative modeling strategy, is that it also remembers irrelevant things. And then we have this notion of what's called nuisance novelty, which is you get a lot of false alarms due to changes in the images that are in the background. They're really unimportant. And so another big open problem is, what kinds of knowledge does our system need to have in order to reason about whether an anomaly is actually relevant to the task or not? I think if we were thinking about the self-driving car, if it can reason about things that are stationary in the sense of non-moving objects in the background, should be irrelevant. It's really moving obstacles in the foreground on the road that are going to be a challenge. That kind of knowledge is the kind of thing we would need.
Mm-hmm. Okay, so I have one last question for you. So from the audience, so would it be possible to exploit the learned feature weights to generate samples which are inverse to them?
Yeah, so that's one thing that actually I thought you were going to ask me earlier. What are some strategies for kind of generating pseudo anomalies? Let's try to take, say, our training data and transform it to generate outside. And so a lot of those strategies have been explored. I had a paper with a student of mine, Dan Hendricks, who's now a PhD student at Berkeley, and we developed this technique called outlier exposure. And the idea was, at least in computer vision, you can pull down all kinds of images off the web and treat them as candidate outliers without labeling them. Another thing you can do is to try to use generative models to generate extreme, extrapolate outside your training data set. And my colleagues Xiaoli Fern and Fuxin Li and some of their students use generative models to interpolate among known images and try to extrapolate from them, counterfactuals. There's work on these instance level unsupervised or self-supervised techniques where they use some transformations. There was this paper called, I think, what is it? Now I can't remember, SCI maybe, where they use perturbations like image rotations to create out of distribution training data and train the network to represent that, but to raise an anomaly score when they see it, kind of thing. So that's another powerful strategy, because we can bring in domain knowledge to say what kinds of image transformations should leave the output unchanged, because they're invariant, and which ones should cause a change in the behavior of the system, say this is something different.
Okay, thank you very much. It was a great pleasure to listen to your talk and also to discuss with you about this important topic. So thanks a lot. And
you're welcome. And I invite people in the audience. I gave my my Twitter handle at the beginning. It's TDietrich. If you can send me a direct message if you have other questions you'd like me to answer. Be happy to follow up. Okay. Well, thank you very much.
Thank you.
Thank you, Wojciech, and thank you also very much, Professor Dietrich, for your very interesting talk. We hope that you enjoyed the presentation and the discussion, and we're going to put a quick poll on the screen. And in the meantime, let me also mention a few things that may be of interest to you. So on next Tuesday, we have a webinar on using satellite imagery and machine learning using QGIS. And on Thursday, we have the next talk in our Trustworthy AI series on adversarial attacks and defenses with Alexander Madry of MIT, again hosted by our host here, Wojciech. We hope that you'll be able to join us there. And goodbye.
Selector, rewind selector, rewind selector, rewind selector, rewind selector, rewind selector. Selector, rewind selector, rewind selector, rewind selector, rewind selector, rewind selector.